Hi everyone, in today's video I'm going to be going through the first exam from Math 115 at the University of Michigan from fall 2019. And most of my explanations are going to be problem specific, but every now and then I'll talk a little bit about how this problem fits in with a typical exam and just sort of what to expect generally. So let's go ahead and get started. The amazing Wanda is performing a magic act. Let V of t be the volume in decibels of the audience's applause t seconds after beginning the act. At time 0, the audience is already clapping at 52 decibels. Oh, another thing I'm going to be doing throughout is highlighting stuff. So at t0, volume is 52. Wanda's trick lasts 45 seconds. The volume of the audience's applause increases at a constant rate of 0.4 decibels per second. Write a formula for V of t. Okay, so constant rate, that's a keyword. That means this is linear. And this would be the slope. If it's a constant rate of 0.4 decibels per second. And we also see that initially at t equals 0, this is the volume. That's going to be the y-intercept. So the way they've described this scenario, they've really already given us the two values in y equals mx plus b. They've given us m and b, so we'll just fill those in. 0.4x, but not x. This is an important point. We want to use the right variable names. So 0.4t plus 52. Okay. The second part of this, during Wanda's second trick, which begins at t equals 45 and lasts until the end of the act at 95, the volume of the audience's applause increases 1.2% every second. That sounds like an exponential rate, and it goes from 45 to 95. Now we want to write a piecewise formula for V of t on the entire interval 0 to 95. Make sure V of t is a continuous function. Okay, well, we already know what it looks like from 0 to 45. We figured that out in the previous part, and so that just amounts to filling it back in. So that's a little bit tricky. People will often overthink that kind of thing, but sometimes it's just as simple as saying, all right, we already know what it is for 0 to 45. From 45 onwards, we know this is going to be exponential. And based off of the rate they're giving us, this 1.2% every second, we know that the a term is 1.012. So we'll have something like that. And then we'll have like a p naught out front. And so the last thing we need to do is figure out what p naught is, and there's a number of ways to do it. I want to try to do it in a way that makes it clear that there's a little subtlety to this problem. So, okay, we know that initially the volume is 52. It increases linearly by 0.4 decibels per second up until 45. So the first thing I want to know is, what is this height, right? Because then it's going to continue on exponentially. It's important to know what height we're at when t equals 45. We can get that by just plugging in 45 to this equation. So we'll do 0.4 times 45 plus 52. Now I have to grab my calculator. So that's 18 plus 52 is 70. And so here we're at a height of 70. And a lot of people would then say, okay, this answer is 71.012 to the t. However, if you graph this function, this would have an initial value of 70. It would look like this graph here, except it would start at 0. It would look like that. So what we need to do is take this one that we found. We need to shift it over 45 units, because this exponential, its initial value doesn't happen at 0, it happens at 45. So the way we can shift this to the right by 45 units is to, instead of having t up here, have t minus 45. That's the way that'll work. All right, part B. A few minutes after her act, Wanda returns to the stage for an encore performance. Let W of S be the volume in decibels of the audience's applause S seconds after the encore begins. Could W be exponential? Circle your answer below. Show your work to justify. Alright, could it be exponential? So the important property of exponentials, and really anytime you're dealing with exponentials in a table, this is usually the property you're going to be looking at. It's that the ratio of y values, so the ratio of y values here, 3.6 to 3, that would have to be equal to the base a raised to the difference in x values, a to the 2 minus 0. And there's a good algebraic reason for that. I won't go into that right here. Leave me a comment or reach out to me if you want to understand this a little better. But just to do it quickly, the difference in x values, if we take the base, raise it to the difference of x values, it's the ratio of y values. So these first two data points would tell us that a squared equals 3.6 over 3, which is 1.2. The second pair of data points would say a to the 3 minus 2 equals 4.32 over 3.6. And if we simplify that, that would say a to the 1 equals, and when you take this ratio, it is also 1.2. So one equation, if this was exponential, we would have one equation saying a was the square root of 1.2, coming from that one. And then coming from this one, just a equals 1.2. So we're getting different a values depending on the pairs of points we're choosing, and so this can't be exponential. Right? We would need some consistency. We'd need to be finding the same a value regardless of the points that we take. Let's move on to problem 2. On the axes provided below, sketch the graph of a single function h of x that satisfies all of the following conditions. And I'm not going to read these all out before getting started. Let me just say something a little general about these kinds of problems, and then we're just going to try and do it straight through. So it's typical for these data points to move in a left to right fashion, so that it's reasonable for you to do each point individually and then kind of check that everything works out. Some other things, okay, so I like to quickly scan through and see if it gives us any hard and fast values of h of x. So here it says h of x has a y-intercept of -3. That means I'm going to put a point there at the y-intercept of -3. And that's just to get us those anchor points, things that we know have to happen. Other ones can come from these, like limits. Like if you look at these limits here, it says limit as we approach -5 from the left is 1, limit as we approach -5 from the right is 1. So for now, just at -5, I'm just going to put like an open hole to sort of indicate that the limit as we approach, we don't know how it's going to approach exactly, but just that we have to be approaching 1 around this value of -5. Maybe we're going to fill in that hole, maybe not. First condition is typical. Domain is -8 to 8. That's just to make sure that you draw the entire function. So let's not worry too much about that. h of x is concave up and decreasing on -8 to -5. Concave up and decreasing. So this is concave up, has a sort of U shape. And to be decreasing would be to be the part that's curving down. So we're expecting this kind of shape. Let's just do that. So there it's concave up and decreasing. So we've got that checked off. Already thought about this limit one. H of x is not continuous at -5. So that means even though these limits agree on the left and the right, it shouldn't be continuous, so we need to have some kind of jump discontinuity. Let's go ahead and just put one in. Doesn't really matter where it goes as far as I can tell. And sure, let's just go ahead and fill in like a straight line there. So now like the straight line has really, we could have done anything, like whatever. But straight lines are the easiest things to draw and the simplest, so I'll just put a straight line. So now those limits both agree. Now let's look at this point. H of -4 minus h of -2 over -4 minus -2. The key idea in this point is to recognize that this is the equation of a slope. This is the slope from -4 to -2, and it's supposed to equal 1. So that means if we look at our value at -4 and then we look at our value at -2, overall the slope has to be 1. It doesn't have to be constant, like a constant slope. It doesn't have to be linear or anything. It can increase whatever way we want. You could even do something like that. But as long as it starts in one place and then it goes over 2 units and up 2 units, we're all good. So that's done. We got the y-intercept. H of x equals h of -x from -2 to 2. So it's key to recognize that this is the formula for an even function. So to have even symmetry, which means whatever happens on the negative side happens on the positive side. So let's just do that, and let's do it simply. So let's just have a linear function come down to the intercept. And then to make it even, the same thing has to happen on the positive side, so we'll come back up. So now we're symmetrical across the y-axis. So that's all good. And then on the interval 3 to 8, the function h of x is the derivative of the function g of x shown to the right. So we want to sketch the derivative. From 3 to 8. We're not at 3 yet, so again, I'll just put in like a flat horizontal line. And now we're going to start sketching this. Okay, so looks like the derivative here is 0. Oh, actually, it doesn't say anything about continuity. Domain. Nope, doesn't say anything about continuity, so that's fine. So we'll put an open hole there. And this is a really subtle point. It says the derivative, so it's the derivative on 3 to 8 not inclusive, which is why I'm putting an open hole here. And it says the domain is -8 to 8. So this whole function has to be defined on the entire interval, so I'm going to put a closed hole there. We could have also just not had to deal with this funkiness. If I just made the slope like that, we wouldn't have to have worried about the jump. But either one is okay. So now the derivative looks like it's 0 from 3 to 4. Then it looks like it quickly goes down to being, that looks like a slope of -1. It's going to quickly go down to -1. It doesn't have to be this extreme. Probably anything that just kind of slopes down and gets to -1 would be good. And then as we're going from 5 to 6, it looks like the slope gets a little less negative. It's -1/2 here. So it's going to come up and be like -1/2. Something like that. And I guess I should keep that straight all the way to 8. Okay. So this is an answer. This is something that would score full credit. It's just important to know that there's always more than one right answer to these problems where you're sketching a graph. And so it's important not to get hung up on being worried about doing exactly the right thing. You don't have to do exactly the right thing. There's many right things to do. And so just have confidence going in that you can find a correct answer. All right, let's move on to problem 3. Horatio the Daring is performing a dangerous stunt. Helicopter A and B are circling around Horatio to film the event. So it's showing us in this picture. Looks like that's one of the helicopters. This is another helicopter. They've got these arrows. Let T be the amount of time in minutes since the start of Horatio's stunt. A top-down view of the flight path is shown at the right. The locations at T equals 0 are labeled A and B. We see those. All distances are measured in kilometers. Helicopter is flying counterclockwise. That's why these arrows are going this way. That's counterclockwise. In perfect circles. Okay. Helicopter A moves at a constant speed of 0.7 kilometers per minute around the circle of radius 2.1 kilometers. Write a formula for the function a of t that gives the y coordinate of helicopter A at time t. So that's a lot of words, a lot of qualifying statements. Let's try to break this down and highlight some stuff. It's moving at a constant speed. This is the radius 2.1. And then we want a formula for a function a of t that gives the y coordinate of helicopter A. So let's just sort of think through as a thought experiment what's happening to the y coordinate of helicopter A. So it starts off and it's up here, right? Here's the starting y coordinate. And based off this radius being 2.1, I'm going to do this in a different color just so it pops a little better. 2.1. So this height initially, this y coordinate is initially 2.1. I'm going to graph a of t. Just sketch it. Starts off at 2.1. And then it travels and the y coordinate's going down, it's going down, it's going down, it gets to 0. It continues as the y coordinate becomes negative until a is down here at negative 2.1. Right, and now it's going to start traveling up. The y coordinates are going to start increasing, so it's going to increase, 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 get to 0. This is where it would be 0 again. And then it'll come back all the way up to 2.1 and get to where it initially started. So that's one period. And we can already determine a lot of things about this function. It's periodic, it starts at its maximum height, and that maximum height is 2.1. That immediately says, since it's starting at its maximum height, I'm going to use cosine. Since its maximum height is 2.1, or I should really say since its amplitude is 2.1, there should be a 2.1 out front. Cosine bt. B is related to the period. We haven't figured out anything about timing yet, so I won't fill in b. And then the other thing is the mid value, right, of this. The average value of this trig function is 0. It's not shifted up or down. So there's nothing to add. You're just adding 0. Okay, so this is already really close to the final answer. And it's just from recognizing it starts at its maximum height. Its maximum height is 2.1, and it's oscillating around 0. Now to find b. B is 2 pi over the period. And so we need to figure out the period. The period is how long it takes for this helicopter to make one full revolution, right? One full cycle. We know that this is the speed. It's going it's going 0.7 kilometers per minute. The radius is 2.1 kilometers. So then what is the circumference? What is the distance that this helicopter actually has to travel? The circumference is 2 pi times the radius, 2.1. So 4.2 pi is the circumference. And if it's traveling at a speed of 0.7 kilometers per minute, the time it takes for one revolution, the period, is that distance divided by the speed. If we do that division, it's going to be 6 pi. So now we're going to have a good formula for b. b is 2 pi over the period of 6 pi. That's a third. So the pi's cancel out. That's kind of nice. There's our final answer. Moving on to part B, the x-coordinate. So now we're thinking about the x-coordinate of helicopter B. At time t is given by the formula, that one right there. Find all the values of t during the first hour of the stunt at which the location of helicopter B has an x-coordinate less than or equal to -3. Give your answer as one or more intervals with endpoints in exact form. Notice this is a 6-point question, so expect that this is going to take a few minutes. It's not a gimme by any stretch. I like graphing things. I think that helps thinking through just what we're trying to find and what we should expect out of the solution. It's a negative cosine graph, and so it's starting at its minimum, and we can verify that visually. We notice that b starts at its lowest x value. The x-coordinate is the smallest it could be, and then as we go this way, the x-coordinates are going up. So this is what the graph's going to look like as it cycles. And down here we're at -3.8, and here I'll write in -3. I'll write it like a dashed line. And I don't know yet exactly like what times these are, and I don't know where time t equals 60. So right, I think it's the first hour, so we're 60 minutes. I don't know exactly where that happens on this graph yet, but just to give you an idea of the solution, we want to know all the times where the x-coordinate is less than or equal to -3. So like down here it's less than or equal to -3, and down here it's less than or equal to -3, and then probably nowhere else before 60. But it even might get cut off over here. The idea then is to find these points to know at what exact times it's equal to -3, and then to write the intervals out using these points, because we see it's like 0 up to whatever this time is, and then this time up to this time. So we want to know what these times are. And here's just where the period ends. First thing, I want to get a handle on what the period is. You might do this in a different order on the test for yourself, but I kind of know it'll be good to think about to start. So if b equals pi over 32, the period is 2 pi over b. These will cancel, those will multiply, and we'll get 64 minutes. Okay, so that means this time right here is times 64, which presumably means that we're going to get cut off here. Like, we're not going to have this whole interval. We're just going to go from whatever this time is up to time 60. Okay, let's go ahead and solve for these times finally. Okay, so we have a formula. We want to know when it equals -3, so we'll just set it equal to -3. If you notice, it does ask for things in exact form, which means we really should be avoiding our calculator for the most part in this problem. So we'll divide, cancel out those negatives, and we get to an equation like this. And the way to move forward at this point is to take cosine inverse. And hopefully you learned in class that when you take cosine inverse, it will give you this point, the very first point, when you solve for t. So t is 32 over pi times that cosine inverse. So that's this time. Let's call that like t naught. That's t naught. That's the first time it's -3. When is the second time it's -3? For that, you need to employ some symmetry. So this distance right here, from 0 up to the first time, that's equal to the distance between the second time and 64. So if this is t0, we'll call t1, that'll be 64 minus this big equation, 32 over pi cosine inverse 3 over 3.8. Now at this point we could just guess and come up with an answer, an interval based off of these numbers, but we really should check what this value is as a decimal to make sure that this number is below 60. So I'll do that. And it will just take me a second here and I'll report the answer. That seems bigger than I was expecting, but is that right? Oh, nope, that is bigger than it should be. Good, okay. So this number is about 6.7. So this number is less than 60. This number is like about 57.3. So then our answer, see, less than or equal to -3, will go 0 up to this first point. And then a u to say and, that's how you combine intervals in interval notation, up to 64 minus. If I had to pin down the most important aspects of this problem, it's using inverse cosine, or really using inverse trig. That comes up, that always comes up on the first exam, and using the period to come up with this symmetry. You find the first point using inverse cosine, and the second point comes from period minus the first point. Problem 4. Portion of the graph of a function is shown below. Note that f of x has a vertical asymptote at x equals 2. We're going to describe or select some properties of this function. For which of the following values of a is f of x continuous at a? So continuity means that the limits from the left and right agree and they're equal to the value of the function. So at -3, is it continuous? I guess another more intuitive way of saying continuous is that you can draw through that point without picking up your pen. So at -3, yep, it's continuous. At -2, no, it has a jump discontinuity. At 1, yep, it's continuous. At 3, no, it has another jump. For which of the following values of b is the limit of f of x as x approaches b from the right equal to f of b? So if you look at what the function is approaching from the right, does it equal the value of the function? -4, it does, because it's continuous there. So as we approach from the right, I'll use a different color. As we approach from the right, it equals the value. So yes, at -2, we approach from the right, it doesn't equal this jump value. 0, as we approach from the right, it equals the value. 3, as we approach from the right, this is the trickiest one, as we approach from the right, it does equal this value. So it's because the hole is closed up on this side, so that as you come from the right, it equals this quantity. So yep, there. And I realized my explanation for 1 was incorrect, because now I realize I looked at a equals 0. But it is continuous. This function is continuous at 1. We can draw it. It's not differentiable, but we don't have to pick up our pen to draw at a equals 1. The following parts evaluate each of the given quantities. If it doesn't represent a real number, right, d and e, or does not exist. Limit as x approaches 2 of f of x. As x approaches negative 2. So the limit as we approach negative 2. Well, from the left, it equals 1. And from the right, it equals 1. So the overall limit is 1. Part D, the limit of f of x as x approaches 5. From the left, the limit is 1. From the right, the limit is negative 1. 1 does not equal negative 1, and therefore this limit does not exist. So if the left and right limits disagree, limit does not exist. Part E, limit of e to the negative f of x as x approaches 2. So when you have compositions like this, like when you have a function of f of x, you need to try to break it down into parts. So first we should think what's happening to f. Then we'll think about what's happening to negative f. And then finally we'll think about what's happening to e to the negative f. So f of x, as we approach 2, what's happening to f of x? It looks like from the left, it's going up to plus infinity. And from the right, it's also going up to plus infinity. So f of x is going to go to plus infinity. If f of x is going to plus infinity, what's happening to the whole exponent, negative f of x? Well, it's going to go off to minus infinity. And if a number, like e, is being raised to values that are getting more and more negative, going off to negative infinity, this exponentiation is going to go off to 0. So the limit is 0. Last one, limit as h goes to 0 of f of negative 6 plus h minus f of negative 6 over h. The key idea in this limit, and they love throwing in limits like this, is that this is a limit definition of the derivative. This is the limit definition of the derivative of f of x at x equals negative 6, because this negative 6 in here. So we'll go look at negative 6. We're going to ask what's the value of the derivative, which is just the slope of this line. And that slope is negative 1/2. Great. Problem 5. Weather balloon is launched and heads straight up away from the ground. Let r of t be the height in kilometers of the balloon above the ground t minutes after launch. Function r of t is invertible and differentiable. If we look at r, this height above the ground, it's getting larger and larger as time goes on. Part A. On which of the following intervals could r of t be concave up on the entire interval? Okay, so this function r of t is increasing. We know that. We know it's going up. There's a general trend upwards. But we want to know, like, can it be concave up the whole time, or where can it be concave up? In terms of slopes, concave up means that if I look at a slope early on, like for an earlier time, and then a slope for a later time, those slopes have to be getting steeper because I have to have this curving upward effect. So we can start looking at slopes between these points, and as long as the slopes are getting steeper and steeper, we know that it could be concave up. It doesn't guarantee it, but it could be. But if we see that a slope gets less steep, that indicates it cannot be concave up the whole time. So let's look at 1 to 9 first. So we're going to take the slope between t equals 1 and t equals 3. So I'll do 0.4 minus 0.01, and then I'll divide that by, not 0.4. Sorry, I'll do 0.19 minus 0.01, and then I'll divide it by 3 minus 1. And I'll get that this slope here is 0.09. Do the same thing for 3 to 9. 0.4 minus 0.19 divided by 9 minus 3. That's 0.035. So this slope is less steep than this slope, and that indicates 1 to 9. It cannot be concave up on 1 to 9. Let's continue with these slopes. So 9 to 18, I'll get that one, 0.84 minus 0.4 divided by 18 minus 9. I get 0.049. So there, this slope from 3 to 9 is less than this slope from 9 to 18, and so it is possible that it's concave up there. And then for 9 to 35, I need to get this final slope here. So I'll do 2.3 minus 0.84 divided by 35 minus 18, and we'll get 0.086. Again, those are estimates, but we see that the slope is going up still, so it's possible that it's concave up from 9 to 35. Find the balloon's average velocity between the times t equals 3 and t equals 18. So we're going to look at these points, 3 and 18, and we're just going to take the slope between them. It's easy, we've been doing that. How about I'll actually write that down here. We'll do 0.84 minus 0.19 divided by 18 minus 3. And I'm getting that that is 0.0433. And here's a really critical thing to notice. It says include units. So I'll write 0.0433. It didn't say exact form, so I'm fine rounding there. And what are the units here? It's the height in kilometers, t minutes. So we have kilometers and minutes. And so the rate, the top part will be kilometers, the bottom will be in minutes, and so this is kilometers per minute. Part C, estimate the balloon's instantaneous velocity at t equals 63. Show work, include units. Again, this is just about taking slopes. So we see 63 right here. We don't have its instantaneous velocity. That would be the slope of its tangent line. But we can estimate it by taking a nearby slope between 2 points. So since 60 is the closest point to 63, we'll do the slope between these two. We'll get 0.4 over 3, 0.133. And then again, keep an eye out for this, include units. You will lose points if you don't include units. And again, this is just kilometers over minutes. Estimate R inverse prime of 3. Show work and include units. Okay, R inverse prime of 3. So R inverse is the function where you switch x and y values. So we could make like a whole table of it where these rows and where these two rows are switched, but we don't really have to do that. The important thing is just to note that this is the place we're looking at, because this is where we have 3, and R inverse of 3 is 45. So I'll write down a couple points here. We have R inverse of 3 is 45, and then for another nearby point, let's do either one is fine. Let's do that one, 3.7 and 60. So we have R inverse of 3.7 is 60. And so if we want to estimate R inverse prime of 3, we're going to do the slope between these 2 points. So that's change in y, 60 minus 45, over 3.7 minus 3. 21.43. Again, that's an estimate. Notice that all this ends up doing for R inverse prime, it ends up having a reciprocal. The difference on top ends up being what were the x units before. So now they're the y units. So we get this. And just like before, we want to include units. And since it's our inverse, the units flip. The 60 and 45 were minutes. These were, were these minutes? Yeah, these were minutes. These are kilometers. So it's minutes per kilometer. It just ends up being the reciprocal of the other rate. For E, let m of s be the height in meters of the balloon above the ground s seconds after its launch. Find a formula for m of s in terms of r and s. There are 1,000 meters in 1 kilometer. Okay, I'm very excited about this part because I get to show off a thinking tool that a lot of students really like to use to work through these kinds of problems. So I like to think about functions as machines or boxes that have inputs and outputs. So like our original function r, it takes in time in minutes, so it takes in minutes, and it produces height in kilometers. The function that we are interested in is very much related to it. It's measuring the same kind of thing, but using different units. It's going to take in seconds, and it's supposed to spit out meters. So we want to use r in some way and get m. So we're going to build m. One way to think about it is we're building m and using r as one of the building blocks. So here I'll put r down again. It takes in minutes, and it spits out kilometers. But I don't want to spit out kilometers. I want to spit out meters. Not m. I want to spit out meters. So like, if I need to convert kilometers to meters, what is that process? What does that function do? Well, it takes the kilometers, like say 2 kilometers, and it would multiply it by 1,000, and it would spit out 2,000, because there are 2,000 meters in 2 kilometers. And then on this side, I don't want m to take in minutes, I want it to take in seconds. And how do I convert a number of seconds into a number of minutes? I would divide by 60. Right? If I were to say 120 seconds, I would convert that into minutes, so it would be 2 minutes. I would apply the r function to know the height in kilometers, and then I would multiply it by 1,000 to know that height in meters. So m is really these 3 functions composed together. How do we write that down formulaically? We would take our seconds, s, we would divide it by 60, s over 60, to give us minutes. We would apply the r function, as usual to it, r of s over 60, and then we would multiply that value by 1,000. So that's the final answer. 1,000 r of s over 60. Question 6. Shown below at left is a portion of the graph of a function m of x. Shown below at the right is a portion of the graph of a function p of x, which can be obtained from m through one or more graph transformations. Find a formula for p of x in terms of m of x. So transformation problems can be a little daunting because there's multiple transformations going on, and they interact with each other like shifts and stretches. It can be hard to figure out exactly what happens. So I'll try to give you the tools to identify that quickly, and then the tools to describe that in order and write it down as a formula. I like to look at key values like endpoints. So like this point I think is very important. Maxima and minima. So like those points are clearly related. And then end behavior, like asymptotes, horizontal asymptotes. Right? These are just features of functions that we know about and learn about, and they're going to help us to identify what's going on. So if I look at the maximum here, we have a maximum at 3, and it looks like that turns into a minimum of -3 through a process of flipping over the x-axis. So that tells me there's definitely going to be a reflection over the x-axis, which involves taking the y variable and turning it into -y. How about what next? What next? Okay, so these points, the -2 here, this endpoint and this endpoint, they haven't had the same place. Although if we notice, we get to the maximum in the original function. It takes 1 unit, right? As we go from -2 to -1, we climb all the way up to the maximum. However, over here, it takes 2 units. We go from -2 all the way to 0. Right, so this width, to get to the maximum, from the endpoint to the maximum, that x value is twice as large. So we know we're going to also stretch by a factor of 2. Okay. And, oh, this horizontal asymptote is going to lead us astray. That's okay, I'll talk about that in a second. There's one more thing going on. So if we reflected over the x-axis and then we stretched, we would get pretty close to looking like this function, except stretching is obviously going to move this -2 out to -4, right? If I just stretch this function, this -2 would go out to -4. And this -1 would go out to -2. But we notice those happen at -2 and 0 in comparison. So we're going to have to do an x shift to fix that to the right. And I actually think once we do that, this graph will look like this one. And I think actually these don't have different horizontal asymptotes. It's just that because this second one is stretched out, it takes it longer to get down to its horizontal asymptote. So now we want to do these 3. This order is totally fine. The stretch and the reflection don't interact with each other at all. And so we just need to make sure we do the x stretch and x shift in this order, because that's how we talked through it. So this will reflect over the x-axis, doing -m, and then we're going to stretch by a factor of 2. And remember, for x units, that means multiplication by half. It's the opposite for y units, which is always tricky. And then to do the shift, I then put in parentheses, and I'm going to shift it to the right, so I'll do x minus 2. So when you're doing x transformations, in order, you do them as close to the variable as possible. So you would do this 1/2, but then you would do the shift just to the x variable. So doing this 1/2 x minus 2 on the inside, this would be incorrect. So when you're doing changes to the x variable, in order, you do them as close to the variable as possible. And it's the opposite for the y. Question 7, for a constant c, let k of x be that whole expression. Use the limit definition of the derivative to write an explicit expression for k prime of 3. Your answer may include the constant c, but shouldn't involve the letter k. Very standard 5-point question. I'm going to put it right here to begin. Limit h goes to 0. If you leave off the limit in your definition, you'll probably lose 2 points. So you'll get like a 60% on a part of a question that you absolutely should get 100% on. Everyone should get 100% on this. So limit as h goes to 0. That's going to be there. Now I'm going to write the limit definition up here using the value k. So limit h goes to 0, k of 3 plus h minus k of 3 over h. But now we can't involve the letter k. We actually have to plug these numbers into the formula. So we'll go ahead and I'll just do that directly into the box. 2 to the c of 3 plus h over e to the 3 plus h minus c. So that's a lot, but that's just k of 3 plus h. We've plugged in 3 plus h into our x values. Minus 2c3 over e to the 3 minus c. That's k of 3, then all over h. It's okay for this to be a compound fraction. It's no problem at all. They even will tell you in every single one of these, do not attempt to evaluate or simplify the limit. You can simplify it. If it's simplified and right, you'll get full credit, but you'll have wasted some time and introduced the possibility for more algebra mistakes. So I would really encourage you just to leave it very messy. Find the value of c so that k of 1 equals 5. Give your answer in exact form. This is just algebra. We're going to plug in 1 for x and 5 for k of x. But it's algebra involving logs, so they want to test that. 2 to the c times 1, e to the 1 minus c. Okay, so we get 5 equals 2 to the c over e to the 1 minus c. There's a lot of algebra you can do here, so I'm going to do it in one way, but if you have a different way of getting to this, that totally is fine. My method is the following. So I would, what's going to be the easiest? I would take natural log of both sides. I'm going to do ln of 5 equals ln of 2 to the c over e to the 1 minus c. And now it's going to boil down to carefully applying log rules. So first I know ln of a fraction is ln of the top minus ln of the bottom. So that's ln 2 to the c minus ln e to the 1 minus c. Then I know I can pull out exponents in front with logs, so this is c times ln of 2 minus this is 1 minus c ln of e, and ln of e is just 1, so I can actually just get rid of ln of e. And now we're just going to do normal kind of algebra. Collect up like terms. First I'll distribute the minus. So ln of 2 times c minus 1 plus c. I'll move the negative 1 over. I'm sure this is incredibly boring for me to describe in these minute details, but it is tricky. I'm going to factor out the c on the right. Ln of 5 plus 1 equals c times ln of 2 plus 1. And then I'll divide by ln of 2 plus 1. So c equals ln of 5 plus 1 over ln of 2 plus 1. Definitely there's a chance I made a small algebra mistake in there, but it looks right for me right now. This is the kind of work they're looking for, by the way. Show all of your work. We're down to 3 more problems. Problem 8 is about interpreting equations, and especially interpreting equations involving derivatives. Here we go. The size of a harvest at a kale farm is a function of the total amount of compost the farm uses in the fields. Let K of C be the size measured by weight of the farm's kale harvest in tons when it uses C cubic meters of compost. Here the little box notation or little machine notation is going to make another appearance. And that's because we're doing interpretation questions with units, so I want to really keep track of units here. C is in cubic meters of compost, meters cubed. And K of C is the size measured by weight in tons. So there, it spits out tons. Let P of H be the farm's profit in thousands of dollars, $1,000, when the kale harvest is H tons. So these functions can be composed together because I can take meters cubed, get tons, then take tons, and get thousands of dollars. That's just a random point that I wanted to note. The functions k of c and p of h are differentiable, and the function p of h is invertible. Using complete sentences give a practical interpretation of the equation p inverse of 86 equals 53. To give a practical interpretation really just amounts to knowing what the units are and then coming up with a sentence that relates those quantities. So we know P takes in tons and spits out thousands of dollars. That means P inverse does the opposite. It takes in thousands of dollars and spits out tons. Well, if it takes in thousands of dollars, that means we have $86,000. That's what's being plugged in. And we have 53 tons. So a sentence could be something like, farm's profit will be $86,000 when their harvest is 53 tons. So really, once we know the units, it's just about thinking again, what exactly is the situation we're in? We're talking about tons of kale harvest, we're talking about profit of thousands of dollars, and then just turning that into a nice and neat sentence. Part B, write a single equation involving Kp and or P inverse that represents the following statement. If the farm uses 1,125 meters cubed of compost, their profit will be twice as large as if they had used 700 meters cubed. Again, the units are really going to help us through this, just in a slightly different way than Part A. So we have meters cubed. That's one thing we're looking at. Meters cubed, this amount of meters cubed, so 1125, and also 700 meters cubed. And then what else are we comparing? Profit. Profit being twice as large. Okay, so we're comparing meters cubed and profit. When the farm uses this much compost, 1125, what's an expression for the profit they earn? Well, we would do the function k of 1125. That will tell us how much kale will be yielded, how many tons of kale will be yielded, and then if we plug that into P, that will give us the profit when we use this much compost. And then this other expression, P of k of 700, that will tell us the profit when we use 700 cubic meters. And the idea is that this sentence compares these two numbers. It says that this amount, P of k of 1125, that profit will be equals twice as large, double what they get when they use 700. The most common mistake is to put this 2 on the other side, and you'll lose probably a point for doing that. But it's important to just sort of double check yourself. Of course, if you're using more compost, that's more fertilizer, you're going to have bigger yields and bigger, well, maybe not necessarily bigger profits, but in this case, bigger profit. Part C, complete the following sentence to give a practical interpretation of the equation k prime of 950 equals 0.2. And then the sentence is, if the farm uses 955 meters cubed of compost instead of 950 meters cubed of compost. I'm going to say this is all about units as well. K, the original K, takes in how much compost? Meters cubed of compost. produces tons of kale. Okay, so that's the original function. K prime, the derivative of a function, it has the same x units, but its y units are the original y units over x units, tons per meter cubed. So now I know 950 is meters cubed. This is saying if we increase meters cubed by 5, how much should tons go up? Well, if meters cubed, if we have an increase in 5 meters cubed, and then we multiply it by the rate 0.2 tons per meter cubed, then these will cancel, and we'll get 1 tons. Okay, so that tells us the value. Now we need to actually complete the sentence. If the farm uses 955 instead of 950, their yield, their kale yield, will increase by approximately, super key word right there, 1 ton. And that's because looking at this derivative and then deducing that like a change in 5 will be a change in 1, that assumes that it's linear over these 5 meters cubed of compost. We don't know it's linear. We're using the linearization, or you could say we're using the derivative to estimate the change over 5 meters cubed. So we don't know it's exactly a ton, but it's going to be somewhat close to 1 ton. Part D, write a single equation involving the derivative functions k prime, p prime, and or p inverse prime that represents the following statement. In order for the farm's profit to be 101,500 instead of 100,000, the kale harvest must be about 0.9 tons larger. So we have a change in profit and a change in tons. What function will deal with tons and profit? P or P inverse. And since it's relating a change, we're either going to have a statement involving P prime or P inverse prime. This is maybe the hardest, the most subtle point on this exam, but we have to decide which one to use, and we can't use both of them. There's only one that's going to work out. And it's based off of the fact that they gave us an exact quantity. They told us some actual values for profit, but they did not tell us any actual values for tons. They told us about a change in tons. They said 0.9 tons larger, but we don't know if that was like 30 tons to 30.9 or 50 to 50.9 or whatever. We didn't get any values for tons, just a change. We did get actual values for dollars. And so we're going to use those, we're going to plug those in. We want to be talking about evaluating a derivative at like 100, so 100,000, right? So we want the function that's going to take in thousands of dollars and produce some ratio of change in dollars and change in tons. So it's going to take in thousands of dollars. Which one of these takes in thousands of dollars? Well, P took in tons, spit out dollars. So its rate takes in tons. P prime takes in tons and spits out dollar per ton. It's the inverse one that we're going to use, because the inverse does this. P inverse prime, and it'll have tons per thousand of dollars. Okay, so we're going to do P inverse prime, and it's going to produce tons per $1,000. So then This statement actually is quite simple once you know the units and what function to use. It's going to say P inverse prime of 100, or you could do 101.5, but we'll just do 100 because it's a little cleaner. That equals, and we want the ratio, change in tons over change in thousands of dollars. So 0.9 tons over, and be really careful, it's in thousands of dollars, so $1.5 thousand. That's the difference between these two. Great. Last two problems should be a bit easier, and we're doing great on time. We would have 25 minutes left to do these last two problems if we were really taking this exam. Problem 9, parts A through C below are not related. You don't need to show work on this page, but partial credit might be earned. A portion of the graph of a polynomial is shown below. Find a possible formula for q of x of the smallest possible degree. It is a polynomial. Assume the key features of the graph are shown. So there's nothing to the left or to the right. This is all the important stuff we need to know. Alright, we notice some roots here. Here's a root at -1. That means we're going to have a factor x plus 1. Here is a double root at 2. That means we're going to have an x minus 2 squared. Here's a root at 4. That means we're going to have an x minus 4. And so this is a 4th degree polynomial that we've got. That's the lowest degree we can do. And then there is a number up here, a. We need it to pass through this point, so we haven't used this point yet. And we're going to use that point to solve for a. So if we plug in 0 for all the x's, we should get out 4 for y. So we should get 4 equals a times, and plugging in 0 for x, we'll get 1, -2 squared, -4. So we'll end up with getting a equals -1/4. That also checks out because this end behavior is negative. They're both going to negative infinity, so we should expect a negative leading coefficient. And you can just leave it like this. There is no need to FOIL it all out. Part B. Find the formula for a rational function r of x that has a hole with an x value of 5, a vertical asymptote at x equals 1, and a horizontal asymptote at y equals -2. So these 3 points will tell us about some factors, some linear factors of the numerator and the denominator. We've got a hole at x equals 5, and so that means we need to have an x minus 5 term on the top and the bottom. Have a vertical asymptote at x equals 1, that means we have to have an x minus 1 term on the bottom that is not on the top. And to be a horizontal asymptote at -2, whenever the horizontal asymptote is not 0, and it's not infinite, so it's like a finite non-zero value, that means the ratio of leading terms is -2, and they're the same degree. But right now, the bottom is an x squared. The leading term would be x squared. The top is leading term just x. So we need to add, first we need to add a factor of x. You could do that by putting any kind of linear term in the top, so like x minus pi, like x plus 7, anything like that, it works. I'm just going to do x because it's the simplest one. And now this leading term is x squared, this leading term is x squared. That ratio would be 1. We need the ratio to be -2 of the leading term, so we'll just put a -2 in the numerator. And that's going to work. That's going to have all of these properties. And again, you don't have to worry about FOILing anything out. Part C, consider the function, that whole messy thing. Find the limit of z of x as x approaches infinity and as x approaches -infinity if the value doesn't represent a real number. can write DNE or does not exist. Alright, so first we'll do infinity, and we're just going to try to break this down into parts. So as x goes to infinity, 4 to the minus x, that's going to go to 0. Right, so we can basically just disregard this term for the limit as we go to infinity. And then the remaining function is a rational function. Everything else looks like a rational function. And so if we look at its limit as we go to infinity, it's the ratio of leading terms, because they're both x squared. And so we see those are -2/3. On the other hand, as x goes to negative infinity, what's going to happen? Well, now 4 to the negative x will go to infinity, will go to positive infinity, and it will go to positive infinity very, very fast. Faster than any of these other terms. It completely dominates because it's exponential and the others are polynomials. The denominator, the other important thing, so this top part is going to plus infinity really fast. The bottom part, what's it going to go to? Well, as we go to negative infinity, this part would be negative infinity, this part would be positive infinity, but the x squared beats out the x. So this is going to go to positive infinity, but slow, super slow. So this ratio goes to positive infinity. But we want to say if it doesn't exist, write DNE, right? And that says including these cases. So we're going to just go ahead and write DNE. Last question. Let W of t be the amount of water in cubic meters in a small pond t hours after noon on a certain summer day. The function W prime, the derivative of W, is graphed below. They're very clear to emphasize this. I'll emphasize it further with highlighting, and you should really, once you read this kind of question, you should convince yourself, you should spend 30 seconds like just telling yourself it's the derivative, because so often we get mixed up. By the time you get to part B or part C, you can easily forget this is the derivative function, not the original function. You can write things down that'll help you remember that. Like, since this is W prime, these y values are in meters cubed per hour. So if I look at a y value, like this y value of 3 up here, it's 3 meters cubed per hour. It is a rate. The y values of this graph represent rates. Let's go ahead and move on to the problem. So at 10 p.m., is the amount of water increasing or decreasing? Circle your answer below. At what rate? Include units. So it's afternoon, so 10 p.m. is right here. The y value is 1 meter cubed per hour. It is a positive rate. So the amount of water is increasing. It's increasing at a rate of 1 meter cubed per hour. And that came from reading off the y value. Part B, over which of the following intervals of t, if any, is the amount of water in the pond constant? Circle all correct answers. Now, if we look at the graph, anytime these y values are not 0, it means there's a rate. Down here, water is flowing out because the rates are negative. They're negative meters cubed per hour. Up here, the rates are positive meters cubed per hour. Water is flowing in. So the only way you can get to this situation where no water is flowing in or out is where the rate is 0. So at this spot right here, and this spot right here, pen's freaking out, and this spot right here. So 0 to 1 and 8 to 9. 0 to 1 is given as one of the options, so that's correct. These other ones are not, and they just don't include the 8 to 9 option. Over which of the following intervals of t, if any, is the amount of water in the pond decreasing at a constant rate? Circle all correct answers. So anywhere it's below the x-axis, those are places where the amount of water is decreasing. But to be decreasing at a constant rate would be for it to have a flat slope here. Right? That would mean it's decreasing at a constant rate of 2 meters cubed per hour. Nowhere is that the case though. When we're down here, the rates are not constant. They're changing all the time. So the answer is none. Part D, at which of the following times is the amount of water in the pond increasing the fastest? Circle the one correct answer. So where is it increasing the fastest? Again, it's really easy for folks to say, start looking for the slopes here. But that's not what you want to do. You want to look at y values, right? This is already giving you rates. So the place where the rate is the highest is the place where this function is the highest. So up here, and that looks like t equals 7. Final question. At which of the following times t does the pond contain the least amount of water? Circle the one correct answer. Where it contains the least amount of water. So here we have to reason through what's going on with water flowing in and out based off of thinking about these rates. Okay, so we want to think about water flowing in and out based off these rates. So initially, no water is flowing in or out. And then for this whole time period, until we get to t equals 6, water is flowing out of the pond, right? Because those rates are negative. Then we hit 6, and now all these rates are positive. That means water is flowing into the pond here. Nothing is happening from 8 to 9, and then from 9 to 10, again, water is flowing in. So if I start with an amount of water, and then some of it flows out until t equals 6, and then some of it flows in until 12, at what time is my water level the lowest? It's going to be lowest at t equals 6, right? So there we go. That completes the exam. We did it in about an hour and 15 minutes, so we'd have 15 minutes to spare. I know some of this felt like I was going through it fast, but just keep in mind that there were also a number of times where I sort of stopped and talked a little more generally about the problem and went through things more slowly. So totally doable in an hour and a half. There's absolutely some gamesmanship that gets involved, and I don't really go into that in these videos, but I would be happy to talk about that kind of stuff in other ones. But for now, I'll just sign off and say see you next time.